Hello and welcome back to the mechanical studies. In this video, we'll study isobaric process, which is basically a constant pressure process. And remember, here we are studying non-flow process. That means this process executes in a closed system where the system consists of a fixed mass of the working substance. Okay, so let's begin. As I said earlier, isobaric process is a constant pressure process during which pressure of the working substance remains unchanged, or we can say the pressure of the entire system remains unchanged, while other properties of the system like volume and temperature vary. To understand this, let's take an example of heating of gas in a piston cylinder device. So here the gas enclosed in piston and cylinder vicinity forms a system whose one of the boundaries that formed by the piston is movable, whereas rest of the boundaries are fixed. Now as the gas is heated with some external source here, obviously the temperature of gas increases and it expands. Since one of the boundary here that formed by the piston is movable one, the system allows here the expansion of gas, and thus here on heating the volume of gas increases with temperature. You can see here the piston moves upward, allowing the expansion of the gas. Thus with temperature, volume of gas also increases here, and as a result of that, pressure remains fixed, pressure remains fairly constant. This is how the constant pressure non-flow process executes. Now let's consider here 1 and 2 as initial and final condition of the gas, or initial and final condition of the system. Initial condition of the gas or initial condition of the system now can be identified with properties like pressure P1, volume V1, temperature T1 and entropy S1, whereas the final condition after heating of the gas can be identified with pressure P2, volume V2, temperature T2 and entropy S2. Now with these initial and final conditions, we can plot this process on property plots. So let's look at the pressure, volume and temperature entropy plots for this process. On pressure volume diagram or pressure volume plot, this process can be represented by a horizontal line 1 to 2, where volume increases from V1 to V2, whereas the pressure during entire process remains same, P1 equal to P2. So the isobaric line is represented, or isobaric process is represented by a horizontal line on pressure volume diagram. On temperature entropy plot, the gas is initially at temperature T1 and entropy S1. When it is heated, obviously its temperature increases from T1 to T2 and its entropy also increases from S1 to S2. So this process, isobaric process on TS diagram, will be represented by this curve 1 to 2. Now remember here one important point, that addition of heat to the working substance always increases its entropy, whereas removal of heat from the working substance, from the system, decreases its entropy. I've already explained this in my previous video, so please take care of this. It will definitely help you in plotting temperature entropy diagrams of the processes. We have studied now the execution and representation of the process on pressure, volume and temperature entropy plot. After this, we'll go to the analysis of the process and we'll see one by one pressure, volume, temperature relationship for this process. Secondly, we'll see work done associated with this process. Then we'll see application of the first law, how the first law is applied for this process. After that, we'll see change in internal energy, change in enthalpy, and finally we'll see change in entropy for the gas undergoing isobaric process, isobaric non-flow isobaric process. Okay, so first we'll come to the pressure, volume, temperature relationship of the system of the gas for this process. Now this process is constant pressure process and this process follows Charles' law. Okay, Charles' law that states at constant pressure volume of ideal gas is directly proportional to its temperature. Okay, so from this proportionality we can write at constant pressure ratio of volume to temperature remains constant. So we can write V by T as constant. Now during the entire process in between the initial and final condition, if we apply this Charles' law, we can write this as V1 by T1. Ratio of V1 to T1 will be equal to ratio of V2 to T2, V2 by T2. V1 by T1 is equal to V2 by T2. So this is what the pressure, volume, temperature relationship for this isobaric process. Now we'll go to the work done associated with this process. So work done, we can find out 1 to 2. Work done associated with process 1 to 2, we can write this as W1 to 2 will be integral of del W from limits, in between limits 1 to 2. Now here this is closed system, the process undergoes in a closed system, that means this is non-flow process, and here only work present is PDV work or moving boundary work, which can be represented as P into dV. We have seen this in my previous video. So del W we can replace with PDV. Now here the pressure is constant, it is a constant pressure process, so we can take this pressure outside and we can write this as P integral of dV 1 to 2. Now integral of dV, it will be V in between limits 1 to 2, so we can write this, and finally we can write W1 to 2 work associated with this process as P pressure into volume V2 minus volume V1. So in general we can write this as W1 to 2 work associated with this process, W1 to 2 will be equal to P into delta V. So this is what the expression for the work associated with isobaric process, and its unit will be joule or kilojoule. Okay, in this way we found the formula for the work done during the isobaric process. Remember, while solving the numericals you have to be very careful about the sign conventions. Okay, so please take care of that while solving the numericals. Third, it's a application of the first law. So we can apply the first law of thermodynamics, which states Q minus W is equal to delta U. This is what the expression of the first law for non-flow process. We have seen this in previous videos. Now here I can write this as Q is equal to delta U plus W. Okay, I can rearrange like this, and here I can substitute W, work done, P into delta V. So I can write this as delta U plus P into delta V. Now see here carefully, this term delta U plus P into delta V. Okay, U plus PV, internal energy plus product of pressure volume, that means flow energy, flow work, U plus PV. This is nothing but enthalpy. Okay, so we can substitute this by change in enthalpy, delta H. So ultimately at the end, what we get here, Q is equal to delta H. Okay, this is what the application of the first law of thermodynamics to isobaric process. So we can say here from this, the heat supplied during the isobaric process to the system increases its enthalpy. Okay, increases its enthalpy. Heat supplied is utilized in increasing the enthalpy of the system. Okay, after this we will see formulae for change in internal energy and change in enthalpy. So here the change in internal energy delta U can be calculated with formula mCV delta T. Okay, and here unit will be joule, and if we write in the specific form, so we can write the change in specific internal energy as CV into delta E. This is what this change in specific internal energy, or we can say internal energy per unit mass. So the unit will be kilojoule per kg. Okay, now change in enthalpy, that can be found out with formula delta H will be equal to mass of the system m Cp, specific heat at constant pressure, into delta T, and this will be having unit joule. Okay, whereas on the per unit mass basis we can write change in specific enthalpy, that is enthalpy per unit mass, that will be equal to Cp into delta T, and its unit will be kilojoule per kg, kilojoule per kg, because this is enthalpy per unit mass. Okay, remember here formula for change in internal energy and change in enthalpy remains same for almost all kind of non-flow processes. mCV delta T, that is for change in internal energy, and mCp delta T for change in enthalpy. At last we will see the formula for change in entropy, that will be written by delta S, and this is given by mass of the system m Cp into log of T2 by T1, log of T2 by T1, log of T2 by T1. So this formula gives change in so this formula gives change in entropy delta S mCp log of T2 by T1, whose unit will be kilojoule per Kelvin. Okay, so this was all about non-flow isobaric process.